We've been using slicing techniques to help us calculate areas in 2 dimensions. We're now going to see what happens when we try to use similar techniques to calculate volumes in 3 dimensions. In order to calculate area, we used a sum of n rectangles to approximate our area. Each of these rectangles had a height given by the function and a width given by delta x. We saw that if we let n go to infinity, taking the limit as n goes to infinity of this sum of areas, we got the exact area of the region defined by the integral from a to b of f of x dx. We can take that idea into 3 dimensions by considering approximating volumes by using the area of various cross-sections. We can approximate our volume by letting volume be approximately equal to the sum from I equals 1 to n of a of x sub I delta x, where a of x sub I is going to represent the area of a cross-section. By increasing the number of cross-sections, we get a better and better approximation of our volume, so that volume is then the limit as n goes to infinity of this sum from I equals 1 to n of a of x sub I delta x, which then means that volume can be written as an integral. Volume is the integral from a to b of a of x dx, where a of x is an area function that represents any given cross-section. In order to solve any volume problem, we need a strategy. What we're going to do is choose our slicing direction so that our cross-sections have as simple an area formula as we can come up with. We'll then identify the shape of that cross-section, express our area as a function of either x or y, depending on the direction we've chosen to slice, set up an integral with appropriate limits, so that our volume is either the integral from a to b of a of x dx, or the integral from a to b of a of y dy, and then we'll compute that integral using appropriate integration techniques. Let's start by trying to calculate the volume of the solid we see here. The base of this solid is bounded by the parabola y equals negative x squared plus 4 in the first quadrant, and we know that each cross-section is a square when cut perpendicular to the x-axis. The first step in our strategy is to choose an appropriate slicing direction. We choose to simplify the area formula. Our first option is to slice perpendicular to the x-axis, in which case we get square cross-sections as shown here. If instead we opt to choose to slice perpendicular to the y-axis, we get a cross-section of unknown area as shown in the picture here. Since we know the area of the cross-section when we slice perpendicularly to the x-axis, that is the option that we will choose. Now that we've chosen our slicing direction, we need to identify the cross-section shape and come up with a formula for the area. Here, we'll sketch the region that bounds the area of our shape. Then we'll identify one slice and figure out what the area would be for that particular slice. Here we see, if we choose a slice C, that the height of that slice is given by the function itself, which means it's negative c squared plus 4. That tells us then that the area of that cross-section, which we know is a square, must be given by negative c squared plus 4, all squared. Now that we have an appropriate formula for the area of any cross-section, we need to figure out the limits of integration in order to set up our integral. Because we're slicing perpendicular to the x-axis, we can see that a is going to be our leftmost value and b is going to be our rightmost value. In this case, a is 0 and b is 2. So our volume now becomes the integral from a to b of a of x dx, where a of x is the area of any cross-section. So this is the integral from 0 to 2 of negative x squared plus 4 all squared dx. The last step in our strategy is to compute the integral itself. We know that our volume integral is going to be the integral from 0 to 2 of negative x squared plus 4 all squared dx. Expanding that out, we get the integral from 0 to 2 of x to the 4th minus 8x squared plus 16 dx. Taking antiderivatives, we get 1/5 x to the 5th minus 8/3 x cubed plus 16x, all evaluated from 0 to 2. Plugging in 2, we get 32/5 minus 64/3 plus 32. Plugging in 0, we get 0. Getting ourselves a common denominator, we get 96 over 15 minus 320 over 15 plus 480 over 15. Adding those up, we get 256 over 15, which simplifies down to 17 1/15 cubed units. Let's take a look at another example. This time, instead of having a fixed region for our base, we're going to take a region in the first quadrant and rotate it around the x-axis. That region is given by the function f of x equals negative x squared plus 5x plus 4. Our first step is to choose our slicing direction, again to simplify our area. We can see here that if we slice perpendicular to the x-axis, our area is going to look like a circle, but if we slice perpendicular to the y-axis, we once again get an unknown cross-section. Now that we've chosen our slicing direction, we can figure out the area for an arbitrary slice. We'll pick a value c on our x-axis and look at the slice there. By examining the function sitting in the xy plane, we can see that the radius of this slice is given by the function itself. In other words, when we choose our slice c, the radius of the slice, the circular slice generated at c, is going to be equal to negative c squared plus 5c minus 4. This gives us a formula for the area of any cross-section. We can see that for every disk that we create, the area of it is going to be pi times negative c squared plus 5x minus 4 squared, using the formula for the area of a circle. Now that we know our area function, we can begin to set up our integral. We know that volume is going to be the integral from a to b of a of x dx, where a of x represents our area function. So that's going to be the integral from a to b of pi times the radius of our disk squared, which in this particular case, we can see we go from 1 to 4, pi times negative x squared plus 5x minus 4 dx. Now that we know our integral, we can begin doing our computations. So our volume here is going to be the integral from 1 to 4 of pi times negative x squared plus 5x minus 4 all squared dx. We can move the pi out to the front, so that gives us pi times the integral from 1 to 4 of negative x squared plus 5x minus 4 all squared dx. Squaring our integrand is going to give us pi times the integral from 1 to 4 of x to the 4th minus 10x cubed plus 33x squared minus 40x plus 16 dx. Now we're going to take our antiderivatives. This gives us pi times x to the 5th over 5 minus 5 halves of x to the 4th plus 11x cubed minus 20x squared plus 16x, all evaluated from 1 to 4. We're going to get a lot of fractions now. We see that plugging in 4, we get pi times the quantity 4 to the 5th over 5, which is 1024 over 5, minus 5 halves of 4 to the 4th, which is 640, plus 11 times 4 to the 3rd, which is 704, minus 24 times 4 squared, which is 320, plus 16 times 4, which is 64. Plugging in 1, we get 1/5, minus 5 halves, plus 11, minus 20, plus 16. Distributing our negative sign, moving around some terms, we're going to get pi times 64/5 minus 47/10. 64/5 comes from our first set of parentheses and 47/10 comes from our second set. And that simplifies down to pi times 128/10 minus 47/10, which gives us a final volume of 81 pi over 10 cubic units. If you want a decimal approximation for that, that's about 25.45 cubic units. Now let's take a look at an example where our rotation axis is vertical. This time we're going to rotate the parabola y equals x squared between 0 and 2 around the y-axis. We'll proceed as before, determining which way we want to slice in order to find a cross-section that has the simplest area. We see here if we slice perpendicular to the y-axis, we get a circle-shaped disc. However, if we slice perpendicular to the x-axis, we get a cross-section whose area is not easy for us to figure out. Now that we know we want to choose our cross-sections by slicing perpendicular to the y-axis, we're going to identify the formula for the area. We can graph the function we're given, y equals x squared, and on that graph we'll choose a representative slice at a y value of c. We'll once again use our function in order to determine the value of our radius. We know here that c is equal to x squared. Solving that for x gives us that x is equal to the square root of c, which tells us that the radius at this particular point is going to be equal to the square root of our value c. Since our cross-section is a disk, we can then conclude that the area of the cross-section is going to be given by pi times the radius squared, which is pi times the square root of c squared, which is pi times c. Now that we know our area at a particular cross-section, we know that the area in general is going to be pi times the square root of y squared, which is pi times y. We can see that our a value is going to be 0, our lowest y value, and our b value is going to be 4, the upper limit of the y values. And we can use those to set up our volume integral. Volume is going to be the integral from a to b of a of y dy, which in this particular case is the integral from 0 to 4 of pi times y dy. Our last task is to actually compute the integral to get the volume. So our volume is the integral from 0 to 4 of pi y dy. We can move the pi to the outside since it's a constant. We get pi times the integral from 0 to 4 of y dy. That is pi times y squared over 2, taking an appropriate antiderivative, evaluated from 0 to 4, which gives us pi times the quantity 16 over 2 minus 0, which is 8 pi cubic units. In this next example, we're going to simultaneously rotate two curves around the x-axis. We'll see this time that our cross-section has a slightly different shape, but we can still continue to use the same problem-solving strategy in order to calculate the volume of this solid. Here we have the curves f of x equals x cubed and g of x equals x being rotated around the x-axis. We'll start, as usual, by choosing a slicing direction that's going to give us the simplest formula for our cross-section A. We can see here if we choose to slice with a plane perpendicular to the y-axis, we get an unknown cross-section, something whose area is hard to determine. However, if instead we opt to slice with a plane perpendicular to the y-axis, we're going to get something that looks like a washer. In other words, we have an outer circle and an inner circle, and this is something whose area we can work with. Now that we know our slicing direction, we're going to identify the shape of the cross-section and come up with a formula for A. So we'll graph our two functions. We've got y equals x and y equals x cubed, forming the outer boundaries for our rotation. We'll pick an arbitrary point on the x-axis C to examine our washer shape. We can see that at C we have an outer radius, which is going to be generated by the line y equals x. Then our washer also has an inner radius. That's going to be generated by y equals x cubed because it is the smaller of the two functions on our particular region. So given that, we see that the outer radius is going to be given by c, and our inner radius is going to be given by c cubed. Putting that together, we know that our surface area of our washer which is the shape of the particular cross-section we formed in this case. It's going to be pi times the outer radius squared, which is c squared, minus pi times the inner radius squared, which is c cubed squared. So we see that our cross-section has an area of pi times c squared minus c to the sixth. Now that we know the area of our cross-section, we proceed with our next step, which is to set up the integral with appropriate limits. So our area was pi times the quantity x squared minus x to the sixth. Our volume is then going to be the integral from a to b of that area function dx. We're going to figure out where our two functions intersect each other in order to establish values for a and b. So if we set x equal to x cubed and solve that, we have a cubic equation. We can factor it into x times x squared minus 1 equals 0, giving us that x is 0 or x is plus or minus 1, but we're restricted to quadrant 1, which means we're going to use x equals 1. So now we know that a was 0 and b was 1, so we have the integral from 0 to 1 of pi times x squared minus x to the sixth dx. We've got our volume integral, so now we compute. Volume is equal to the integral from 0 to 1 of pi times x squared minus x to the sixth dx. We'll pull pi out to the front since it's a constant. So we have pi times the integral from 0 to 1 of x squared minus x to the sixth dx. Finding antiderivatives, we get pi times 1/3 of x cubed minus 1/7 x to the seventh, evaluated from 0 to 1, which gives us pi times the quantity 1/3 minus 1/7. We'll get common denominators to get pi times 7/21 minus 3/21, which means that the volume of this solid is going to be 4 pi over 21 cubic units. In our previous examples, we always rotated around the x-axis or the y-axis, but there's no reason we have to do that. So now we're going to take a look at an example where we rotate around a different line. Here we're going to take the curves f of x equals x minus 2 squared and g of x equals the square root of x minus 2, and we're going to rotate those around the line x equals 1 and compute the volume of the solid that we generate. We start off by picking a slicing direction, and we can see here that if we slice perpendicular to the y-axis, we're going to generate a washer shape, which is a shape we know how to calculate the area for, so we'll go with that direction. With our slicing direction chosen, we'll now proceed to attempt to find a formula for the area. We'll do that again by drawing the two graphs in 2 dimensions and using that to help us figure out the appropriate formula. So here we'll graph y equals x minus 2 all squared, along with the graph of y equals the square root of x minus 2. And in this instance, we're also going to have to go ahead and graph our new axis of rotation, which is the line x equals 1. With those graphed, we proceed as usual by picking an arbitrary value of c along the y-axis, which is where we're slicing. And now we're going to look at the radius for c. So we see that we have, because it's a washer, we have an outer radius for our c value, and we also have an inner radius. This time, both the two functions we started with and the axis are going to help us determine what the outer radius and inner radius formulas are. Our outer radius uses the outside formula y equals x minus 2 squared, and we're going to calculate the distance between that formula and the line x equals 1. Before we can do that, though, we have to remember that because we're slicing perpendicular to y, we need to express our functions as functions of y. So we'll rearrange to get that x equals the square root of y plus 2. And now we'll see that our outer radius is going to be the square root of y plus 2 minus 1 to take into account the change in our axis of rotation. That simplifies to the square root of y plus 1. Similarly, for our inner radius, that function is given by y equals the square root of x minus 2. We want to rearrange that so that it's a function of x. We're going to get that x is y squared plus 2. That makes our inner radius y squared plus 2 minus 1 to account for our axis of rotation, which becomes y squared plus 1. From there, we can see that the area of our washer is going to be pi times the outer radius squared minus pi times the inner radius squared, which becomes pi times the square root of y plus 1 all squared minus y squared plus 1 squared. With our area formula understood, we can now go ahead and start setting up our integral with its limits. So our area was pi times the quantity square root of y plus 1 squared minus the quantity y squared plus 1 squared. We're going to expand that out. That's pi times the quantity y plus 2 square roots of y plus 1 minus y to the 4th plus 2y squared plus 1. Combining that all together, we get pi times negative y to the 4th minus 2y squared plus y plus 2 square roots of y. Our volume is, as always, going to be the integral from a to b of our area function dy, because we're integrating along the y-axis. We need to figure out our a and b values. We'll set our two original functions equal to each other, giving us the square root of y plus 2 equals y squared plus 2, subtracting 2 from both sides, and then squaring both sides gives us y equals y to the 4th. Setting that equal to 0 and factoring, we get that 0 equals y times y cubed minus 1, which gives us y equals 0 and y equals y cubed minus 1, or y equals 0 and y equals 1. So now we know that our volume is going to be the integral from 0 to 1 of our area function, which is pi times the quantity negative y to the 4th minus 2y squared plus y plus 2 square roots of y dy. Finally, we compute the integral in order to get the volume. So our volume formula was pi times the integral from 0 to 1 of negative y to the 4th minus 2y squared plus y plus 2 square roots of y dy. Taking antiderivatives, we get pi times negative 1/5 y to the 5th minus 2/3 of y cubed plus y squared plus 4/3 of y to the 3/2. And we'll evaluate that from 0 to 1. Plugging in 1, we have pi on the outside, then we get negative 1/5 minus 2/3 plus 1/2 plus 4/3. Plugging in 0 to all of those gives us 0, so we simplify, we get pi times negative 6/30 minus 20/30 plus 15/30 plus 40/30. And this gives us a final volume of 29 pi over 30 cubic units. Let's recap everything we just saw. We have 3 different methods for finding volumes. The first was general slicing, where we're given a fixed base and told what our cross sections look like. Then we have the disc method, when we revolve around either a horizontal or vertical axis, but the resulting cross sections are circular. And finally, we have the washer method, again revolving around a horizontal or vertical axis, but this time we create a cross section that has a hole in the center. We have a 5-step process for any of these methods. The first step is to choose the slicing direction. Then next you identify the cross-section shape. Express your area in terms of either x or y. Find your volume formula, including any limits of integration. And last but not least, evaluate the integral.